Good morning. My name is Ira Mark Egdahl, and today's talk is on time travel and the fact that although we don't realize it, we do it all the time. You can find out more by going onto my website, marksmodernphysics.com. Brian Greene, a best-selling author and physicist, said that time is amongst the most familiar yet least understood concepts that humanity has ever encountered. And today we'll be talking about a particular aspect of time discovered by Albert Einstein. Time machines are a favorite ploy in science fiction stories. Climb into one, set the dials, press the button, and zap. You disappear into another century. Far-fetched, sure. But are they a real possibility? Physicists are not sure. But what most people don't realize is that time travel itself is a common, everyday experience. We actually experience it all the time, and we don't need a time machine to do it. This all comes from a basic tenet of Einstein's theory of special relativity called time dilation. In Einstein's crazy world, time is not rigid. Per the great physicist, time does not go by at the same rate for everyone. If I am moving at imagine I am moving at everyday speed, walking with respect to you. My watch right now is actually running a tiny, tiny bit slower than your watch because I am in motion with respect to you. Now, it's such a very small amount, we don't notice it, but it is real. Now imagine that somehow I were able to travel at 87% speed of light by you. At that speed, Einstein's formula tells us that my watch will actually run at half the speed of your watch. What that means is that for every second which ticks off on your watch, only a half second ticks off on mine. For example, let's say that I travel around for 87% the speed of light for some time, and come back and we compare watches. Your stopwatch says that my trip took 1 hour. But when we look at my stopwatch, it says that it only took 30 minutes. My watch is running slower because of it's moving at 87% the speed of light. Time slows down with motion. Hard to believe? It does sound crazy. We can only imagine how Einstein must have felt when he first thought of this. It took tremendous guts for him to just propose such a thing. But today we have all kinds of evidence that time dilation, the slowing of time with motion, is a real effect. For example, in October 1971, Joseph Hafele and Richard Keating put atomic clocks on airplanes and had identical atomic clocks on the ground and showed that the atomic clocks on the airplanes ran slower due to their motion. They were also affected by time effects of gravity. And Einstein's time dilation formula was verified to about 10% with this experiment. Several years later, in 1976, Robert Vesset and Mark Levine put a very accurate hydrogen maser clock on a Scout rocket and flew it into the air. And their much more precise experiments verified time dilation to an incredible 70 parts per million. The GPS satellite actually provides us a continuous verification of Einstein's predictions that time is slowed by motion and by gravity. The global positioning satellites that we use to locate places on Earth simply would not work if it did not take into account these time dilation effects. There's all kinds of laboratory evidence also supporting time dilation. For example, in 1992 at Colorado State University, tests for time dilation showed an accuracy of 3 parts per million. What does this tell us? Time is relative. Time does slow down with motion, and in just the amounts Einstein's formula predicts. This tells us that Einstein's crazy universe is in fact our universe. Okay, so what does this have to do with time travel? Imagine it is the year 2950 and you've just purchased your hot new rocket car that is capable of travel at relativistic speeds, that is, speeds that approach the speed of light. You travel into outer space at 87% the speed of light, so time for you passes at half the rate of time on Earth. Now, you record on your watch that the trip takes you 5 years, round trip, going out to a distant star and returning to Earth. What you do is, you look on your watch, and every 24 hours you mark off a day on your calendar. And every 365 days, you mark off a year on your calendar. When you return back to Earth, you find that your calendar tells you it is the year 2955. But here on good old Earth, time is not running slow, like time on your rocket. So when you return, 10 years have elapsed on Earth. In fact, everyone on Earth has aged 10 years. And Earth calendars show it is actually the year 2960. When you alight from your rocket car and step onto solid ground, to you it is the year 2955. After all, you've only been away 5 years, but in your rocket time. But it is the year 2960 here on Earth. So you were away for 5 years, but you've come back to Earth where it is 10 years later. So in effect, you have traveled 5 years into the future. And in principle, if you travel fast enough, you could arrive back on Earth thousands of years into the future. Let's take a look at that. What if you took a round trip from Earth to a very distant star at 99.99999% the speed of light? At that speed, Einstein's formula tells us that thousands of years would go by. So you leave the Earth, you travel at that tremendous speed out to the distant rocket, out to the distant star, you travel back, you return to Earth. I didn't do that right. You return to Earth, and you've been away 1 year. And what you find is, when you return, it is now 2,236 years later on the Earth. You have, in effect, traveled thousands of years into the future in 1 year. Per special relativity, you can, and you do, travel into the future. But you cannot travel into the past. In other words, it is a one-way ticket. Now let's look at everyday time travel, something we experience all the time. Say you leave for work in the morning, and your roommate is sick in bed, and stays in bed at rest the entire day. You drive to work, go into your office, and at night, you return from work. Because of your motion to and from work in your car and any other motion that you experience during the day, time has run a tiny bit slower for you during those periods when you were in motion. Therefore, you actually return home to your roommate a tiny bit into the future. In any time you are in motion, you experience this effect. In fact, every time you leave a place, the slowing of time due to your relative motion means that you return to that place a tiny fraction of a second into the future. So big drum roll here. We are all time travelers.